Hello everybody. In this video we're going to study Riemann approximation. We're going to go through right hand rule, left hand rule, midpoint rule, and we're going to learn how to create Python codes for Riemann sum. Let's begin with the idea behind the Riemann sum. Let x squared be our function that we are computing the area under the curve from 0 to 4. So the idea is to divide the area under the curve into subsections. So we're going to partition the area into rectangles. And the area of rectangles summed will be the area under the curve. For the right hand rule, we pick the rightmost point of the rectangle. For the left hand, we pick the leftmost of the rectangle. And for the midpoint, we pick the midpoint of the rectangle value. Each rule has their advantages and drawbacks, their overestimation and underestimation. So it is good to do all of them and compare depending on the function. So in our example, we have x to the second or x squared, which is our parabola, and we are interested in finding the area under x squared from 0 to 4. We of course can find this using definite integral. Integral from 0 to 4, x to the second dx will give us the exact area under the curve. So antiderivative of x squared is 1/3 x to the third from 0 to 4, and that's going to be 4 to the third minus 0 to the third, which will be 64/3, which is 21.3, repeating. So we know that this is our exact area under the curve. So why do we need Riemann sum? All integrals are not this nice, and we might need Riemann approximation. Now let's see how we use right hand. Our integral, our definite integral from a to b, lower boundary and upper boundary of f of x dx is approximately limit as n is approaching to infinity, summation of the areas of all rectangles, which is I starting from 0 to n, delta x times fx I. Here our delta x is the width of each rectangle, and it is found by b minus a divided by n. b is the upper boundary, in our case it is 4. A is the lower boundary, in our case it is 0. N is the number of the rectangles, and this is totally up to you. You can partition the area into 4 rectangles, or 10 rectangles, or 100 rectangles. And as you subsection more rectangles, the accuracy gets higher. In our case, our delta x is 4 minus 0, and we used 4 rectangles, so divided by 4. So our delta x, which is the width of each rectangle, is 1. But our height vary, because each rectangle has different height. So in the right hand rule, we use this formula because our xi's are the xi's. In the left hand formula, our integral from a to b, fx of dx, is approximately limit as n is approaching to infinity, summation I from 0 to n, delta x times f of xi minus 1, because we would like to pick up the leftmost point of the rectangles each. And in the midpoint, we're going to use this formula. Integral from a to b, f of x dx is approximately summation I from 0 to n, delta x times f of xi minus 1 plus xi, divided by 2. So this is our midpoint in each rectangle. Now let's use our example x to the second and approximate this area using 4 rectangles using right hand, left hand, and midpoint. Our right hand formula will be integral from a to b f of x dx is approximately limit as n is approaching the infinity, summation I from 0 to 4 in our case, delta x is in our case is 1, and fx of I is, that means f of 1 plus f of 2 plus f of 3 plus f of 4 times delta x, because our right points are 1, 2, 3, and 4 in the curve. So what is the value of f of 1? Our f of x is equal to x squared. So f of 1 is 1 squared, which is 1. F of 2 is 2 squared. F of 3 is 3 squared. And f of 4 is 4 squared. Our delta x is 1. So 25, 29, 30. 30 times 1 is 30. So 30 is the answer if we use right hand. And this approximation is little overestimation, because we know that our exact value is 21.3. Let's use the left hand rule. If we use left hand rule, our integral from 0 to 4 of f of x dx, which is x squared dx, is approximately our limit as n is approaching to infinity from 0 to 4 delta x times f of xi minus 1, and xi minus 1 is f of 0 plus f of 1 plus f of 2 plus f of 3, because our leftmost point in each rectangle is starting from 0, 1, 2, and 3. We have 4 rectangles here, and the height of the first rectangle is 0. And our delta x is 1. 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. And this is going to be 14. And 14 is the underestimation. Let's do midpoint rule. According to midpoint rule, our function is approximately I from 0 to 4 delta x times f of xi minus 1 plus xi divided by 2 will be our area under the curve. And this is our midpoint, which is starting from 0.5, and the second midpoint is 1.5, 2.5, and 3.5. Our delta x is 1, and f of 0.5, f of 1.5, f of 2.5, and finally f of 3.5. So f of 0.5 means 0.5 squared, because our function is x to the second. Here, x to the second. So similarly, we're going to set our f of 2.5 and 3.5 times 1, and if you do the algebra here, you're going to get 21. And 21 seems a very good estimation, because our exact value is 21.3. So for this function, midpoint seems the best estimation. But it might not be always midpoint is the best estimation. It depends on the function. So what happens if we use more subsections? What would happen if we divide this area into 10 rectangles, or maybe 20 rectangles, or 100 rectangles. So the more subsections we do, both right hand, left hand, and midpoint estimations get closer to each other, and we get better estimation. Let's do that using the Python codes. Just before we start coding, let's remember how we use Riemann sum approximation for right hand, left hand, and midpoint rule. We use Riemann sum approximation for definite integral from a to b of the function f of x dx as summation I from 0 to n delta x times f of xi, where delta x is the width of each rectangle and delta x is found by b minus a over n, where b is the upper limit of the integral, a is the lower limit of the integral, and n is the number of rectangles we use. So the number n is totally up to us. So if you would like to use 4 rectangles, use n as 4. And the left hand was the leftmost point of the rectangles, so we use f of xi minus 1. And midpoint was the midpoint of each rectangle, so we take the average of leftmost and the rightmost point of each rectangle to find the midpoint. Now, in the light of this information, let's continue coding. We start our coding with our imports. Our first import that we're going to need will be NumPy. And our second import that we're going to be needing will be Matplotlib. Now we're going to write our function f lambda our function is x squared, so we're going to write x squared here, and we're approximating x squared from 0 to 4 and using 4 rectangles for now, and we can increase it after we have finished the function. And let's define n as 4. Let's define x, np linspace requires 3 parameters: a start point, b end point, and number of samples we are generating, n plus 1. And variable y is f of x. Now let's define variable capital X, linspace. We need again 3 parameters: start point a, endpoint b. This time let's use n times n plus 1 to get smoother function. And our capital Y is f of capital X. So our function is x squared, our lower boundary is 0, our upper boundary is 4. We would like to subsection 4 rectangles, and our x and linspace is a comma b comma n plus 1. Our y is f of x, our capital X is a comma b comma n times n plus 1, and our capital Y is f of capital X. And we would like to plot the figure, and we can use the figure size. Let's use 10, 6 for now. We can change it. Now we're going to start coding left endpoints. We're going to use PLT subplot. Very nice function that you can call in once, that 3 inline graphs. So we need 3 criteria here. Parameter 1, which is 1 row, 3 columns, and this is the first column we're working on. Now PLT plot this. We're going to plot capital X, capital Y function we defined above, and we can give a color for it. I would like to use magenta. Now let's define X left and Y left. Our X left is the leftmost point, so it's going to be -1. And our Y left point will be Y -1. So let's plot this. X left, Y left. Let's use the same color, magenta. I'm going to put dot because I would like dot all on magenta color line, and I would like to use marker size 11. So our marker will be dot, and that dot will be 11 points. Now let's plot our rectangles, PLT bar, which is X left, Y left, and the width of each rectangle will be our delta X, which is B minus A, divided by N, which is the number of rectangles we are using. And let's use transparency alpha. Alpha is the transparency. Anything less than 1 is transparent. And let's use align, edge, and let's use edge color. I would like to pick up the same color M. So B for blue, W for white, Y for yellow. You can reach whole library and many more features on matplotlib.org. Let me write it here. So you can check nice tutorials and whole features about graph and lines. PLT bar, and now let's give a title for this plot. I would like to give left end Riemann sum. Let's use n equals to this, so whatever value we give for n will appear here, and let's format it with the variable parameter n. Let's check if our left endpoints are working. If so, we can generate mid and right endpoints. So let's see if that is working. Let's run this code. So linspace is not defined, so it's going to be np.linspace. Let's see this time. Yes, our graph is working. Let's check the size. We can play with the size. Okay, Okay, let's keep it like that first. And you can change the color if you don't like. Let's make it yellow. Okay, let's keep magenta because it's more visible. And our dots are there, and this is the left endpoint. Okay, because this is working nice, so we can generate the right ends and midpoints. So let's go visually left, mid, and right. So we can copy paste this because our codes are working. And we can play on the parameters. So our PLT subplot will be 1, 3, 2 because this is the second column we are working on. 1 row, 3 columns, and this is the second column we are working on. I would like to use the same magenta color, and this time it's going to be X mid and Y mid. Now we're going to average, so it's going to be X mid will be left plus right divided by 2. And our Y mid will be f of x mid. And we need to change the function names because we call it x mid and y mid. And we can use the same marker size, same color. And for the rectangles, we have to change the function names as well. So we're plotting the rectangles with the same width, same transparency, same edge, and same edge color. And let's call it midpoint Riemann sum. Let's see if this is working as well. Yes, they are working nice. So we can generate our right endpoints. Let's copy paste our left endpoints code. Here, this time our parameters will be 1, 3, 3. 1 row, 3 columns, and this is the third column we are working on. And we're going to change the variable name to x right and y right. Our x right will be 1 column, which is representing the rightmost point, and our y right will be y 1 column. Same marker size, same color. We need to adjust the function names we gave. And same delta x. And let's change the title. And let's check this. Okay, they are working very nice. And if you would like to change the size, you can play with the size. Let's check 20,6. Okay. Okay. So our plots are ready. Let's see them bigger. Okay, our left-hand Riemann sum with n equals to 4, our midpoint Riemann sum with n equals to 4, and right end. Because this is increasing function, our right end Riemann sum will give overestimation. If it was decreasing function, then left end points will give us overestimation. Okay, now our graphs are ready. They are working nice. Now let's find the values of each Riemann sum. So let's write some codes for it. Before we start computing the value of each Riemann sum, let's play with our function that we have coded here. So what if we have 10 rectangles? Then we obtain this. Okay, what if we have 20 rectangles? This time we obtain 20 rectangles. So we can divide the section into more rectangles. What if our function, let's go back to 10 rectangles. What if our function was x to the third? And from 0 to 4. Then we obtain this function. What if our function is 1 over x from 1 to 4? So this is what we obtain. So we can change our function, and we can change our lower and upper boundary and number of rectangles. So this is 1 over x from 1 to 4. Now let's go ahead and write some codes that computes the values of Riemann sums. And let's go back to our original question, x squared. Okay. Here we are writing codes that computes the values of Riemann sums. So let's start with dx. dx is our delta x, which is b minus a divided by number of rectangles we use. Our x left is np linspace. Here we have 3 criteria. Our start point is n. Our start point is a. Our end point is b minus dx. This time from the upper boundary minus delta x and up to n. Our x mid or x midpoint is equal to np linspace. Here our criteria is, this time we're starting from delta x over 2 is our start point, because we start from the midpoint of each rectangle, and our endpoint is b minus dx over 2, because we end up in the middle of the next rectangle and up to n. And our x right will be NP linspace. This time we start from the x and we end with b and up to n. Let's print using n rectangles our left Riemann sum will be equal to NP linspace NP sum. So we're going to sum f of x left times dx. Print this time we're going to print left Riemann sum will be our left Riemann sum, the function we have given name. Now let's continue with midpoint. So let's give the name midpoint Riemann sum. And this function will be np dot sum f of x mid times dx, and we're going to print midpoint Riemann sum will be our midpoint Riemann sum that we named above. And for the right Riemann sum, let's name right Riemann sum. That will be NP sum f of x right times dx. And let's print right Riemann sum will be our right Riemann sum that we named above. Now they are ready. Let's check the codes. So our dx is b minus a over n. Our x left is np dot linspace parameters. Let's check if they are working. Yes, they are working. Using 10 rectangles, left Riemann sum is 18.795, midpoint Riemann sum is this, and right Riemann sum is that. Great. Now we can play with the criteria. So let's compare having 4 rectangles and 10 rectangles or 40 rectangles. So our approximation is getting closer. The more rectangles we use, the closer we get, and left, right, and midpoint gets closer to each other. This is using 4D rectangles. How about 400 rectangles? As you can see, we are limiting. Okay, let's go back to 10 rectangles. Let's change the name of the function. Let's change the function. Let's use square root of x. Square root is not defined. Okay. So let's use x to the 1/3, 1/2, which is x squared. This is our square root of x function using 10 rectangles from 1 to 4. Let's use 0 to 4. Let's copy this and see here. This is our square root of x function using 10 rectangles, left, mid and right endpoints. Let's see the values, and this is the approximation. This time let's find the exact value of the area under the curve, writing some integral codes, and then let's find the error. So let's write codes for the error function as well. Here we are going to calculate the exact integral, writing integral codes. So here we are going to compute the exact value. Now we're going to write integral codes. There are different ways of writing integral codes in Python. For x to the second, I'm going to use import numpy as np, and I'm going to define function f of x, and I'm going to return our x to the second as x np dot array. Here I'm going to use one-dimensional array. So our integration in our problem was from 1 to 4, 0 to 4. So we can use 0 to 4. So 0, comma 4. In between, we have to use some value between 0 and 4. 0 and 4 is not accepted. So let's use 3. So the first entry is the lower boundary, and the last entry is our upper boundary. Y is equal to f of x. Here we need scipy, so from scipy dot integrate, we're going to import simps. We can use this either here or at the beginning of the codes as well. So our I will be simps y comma x and print I. So here we are integrating x to the second from 0 to 4. Using 10 rectangles, our left Riemann sum is 4.88. Our midpoint Riemann sum is 5.34. Our right Riemann sum is 5.68. And our exact integral is 21.33. This is merged we changed the function many times, so it merged the answers here. Because 4, 5 and 5 is very bad approximation. Because this is this is square root of x, that's why. So let's go back to our original function x to the second. Okay, as we can see, midpoint Riemann sum is very close to the exact integral here, and as we increase the number of rectangles, left, mid and right approximation is getting closer to each other. So now we have written integral to calculate the exact integral. And here actually we can say the exact value is the exact value of the area. The exact value of the area is our integral. So the exact value of the area is 21.33. Now let's write the error function. So our error formulas will be, here are the error functions. So we can directly print left Riemann sum error will be np dot absolute value of left Riemann sum we defined above minus I. So the left Riemann sum approximation minus the exact value of the integral will give us the left Riemann sum error. Similarly, we can do it for right and midpoint. So right Riemann sum will give us right Riemann sum minus I. Let's use here mid. And let's use right here. Let's check this time. Here we can see that using 10 rectangles, left Riemann sum is this value, midpoint is this value, right Riemann sum is this value. The exact value of the area is 21.33. Left Riemann sum error is 3.09. Midpoint error is this. And right Riemann sum error is that one. So we are good with left, right and midpoint Riemann approximation, finding the exact value and the error function.